All right, so now we are starting Chapter 8. And Chapter 8 is all about parallel lines. So we had a little bit of discussion about parallel lines right at the end of last class, which unfortunately wasn't recorded, by the way. So, oh, you were here. You weren't here, and you weren't here. And you guys are right now. So no need to explain all that again. So Chapter 8, parallel lines. First off, quick definition. I think you already know what parallel lines are, but the exact definition. Two lines, L and M, are parallel if and only if they do not intersect. So if two lines are parallel, they don't intersect. If two lines don't intersect, they're parallel. Right? Okay. And then we have this notation for calling two lines parallel. L is parallel to M is how you read that. And a common way that we represent that with lines, if I have two lines that I'm trying to say they're parallel, common way to mark that is to put arrows on it like that. Those two lines are parallel, and then if I've already used that, then we just do two arrows, and these two lines are parallel. So common notation used for saying things are parallel. So first, let's do a quick proof with parallel lines, and then we'll talk about Euclid's fifth, or the parallel postulate, sorry. Not using Euclid in this class. Anyways, so let's go over it. Theorem 8.1 is, given a line L, so we have some line L, here it is, and some point A not on L. We are trying to prove that there is at least one line through A parallel to L. Okay? That's what we're trying to prove. Big picture, how are we going to do this? Given L and a line, So let's see, how did we start this? We started by taking A and drawing any angle through A, or any line through A intersecting this line. So draw some line through those two. I think the author calls it N, doesn't matter now. Here's just big picture what we're doing, then we'll get exact. So we're going to draw some line through there, making an angle, right? And then we're going to use our existence postulate for angles, which says if you have a ray, which this is now a ray from this point out as a ray, then there's a unique angle we can construct on a particular side of the ray congruent to a given angle. So we're going to come up using this as our vertex, going to the same side that this angle is on. We're going to construct an angle so that those two are the same angle. With me so far? Yeah. Then we're going to assume by way of contradiction that these two lines that they create, wow, that's terrible. These two lines that they create are not parallel, meaning they intersect somewhere. So we're going to assume that they eventually meet up at some point P and go on their merry way, however they go on, doesn't matter. Right? Let me just call this point down here B. So then we have a triangle ABP if these two lines eventually intersect, right? You with me? You see how ABP is a triangle? So if ABP is a triangle and those two eventually intersect to make a triangle, then we have this angle is congruent to this angle, which is an opposite angle inside this triangle, an opposite interior angle of that angle. So remember from last class we proved an exterior angle of a triangle is always greater than either of its opposite interior angles. So we already know that this angle has to be bigger than this angle, and this angle has to be bigger than whatever angle those two would make. So that's our contradiction. Do you see that? Okay, so let's write it down. Well, we use the same picture. Well, draw it as we go. So we're going to start out with some line L and some line A. So 1, let L be any line Okay? So that's how we started out. 2, we're going to pick some random point on this line, call it B, and then we're going to draw the line AB. Let B on L. So we pick some line B on L. There it is. Maybe we want 2 points on L to talk about it, so maybe we'll pick BC on L. So we can talk about that angle. See what I mean?
Yeah.
So let B and C on L, and then we're going to have this line, AB, and then using this angle, ABC, we're going to come up to A and construct an angle congruent to ABC. Good? So what am I going to want to call those points? Maybe we'll call this point D, and we'll pick some other point E. So 3, let E on AB such that BAE, so in other words, E is on the other side of A, and let angle EAD be congruent to angle ABC such that D and C are on the same side of AB. You understand what I'm saying there? So we know that we can construct an angle here. We just can construct one on that side and on that side congruent to this. We want to construct one on this side because we could have just as easily come and accidentally constructed an angle right here instead, which doesn't help us. So we need to do the one using point D that's on the same side of this line AB as C is. So we want these 2 angles to be on the same side of the line AB. That make sense? Okay. So now we do our contradiction. Assume, by way of contradiction, that AD and BC intersect. Intersect at some point P. So assume these guys eventually intersect at some point P. Right? Then angle EAD is exterior to triangle ABP, and angle EAD is congruent to angle ABC. Or maybe we should say ABP, same angle. And that's our contradiction.
Seems like you want to label the line AD M so that you can refer back to what you're trying to prove, right? Because your proof has M in it.
Yeah, that would have been better. Yeah, that's a good point. We should have said let M be the point on that or some line that goes through there on that ray.
Yeah, but
And I also should have started out by letting them intersect and picking the point on the side that intersects. Because this could have also intersected over here. And then we would have been talking about this triangle. But same idea. The overall idea is that angle is congruent to an opposite interior of a triangle if these two lines eventually meet, right? Is that just a whole lot of jargon and you don't know what I just said?
I don't know what you just read.
What's jargon?
So last time, one of the proofs we did is that if we have a triangle and we take, so first off, an exterior angle to a triangle is one that is an adjacent supplement of one of its angles. So here is one possible exterior angle of this triangle. There's 6 possible ones. We could have talked about this one, we could have talked about this one, we could have talked about this one, and then the 2 down here. So every triangle has 6 exterior angles. Its opposite interior angle, so once I have an exterior angle, pick one. We'll talk about this one. Its opposite interior angles are this one and this one. Those are its opposite interior angles. So what we proved is that for any given exterior angle, it's always greater than its opposite interior angles. That was one of the theorems we proved last time. So this angle, the angle outside the triangle, always has to be bigger than the 2 opposite angles inside the triangle. So if this is a triangle, BAP, here's an angle outside the triangle, an exterior angle, here's one of its opposite interior angles. This angle always has to be bigger than this angle. Here they're congruent, which isn't possible, which means that ABP isn't really a triangle, which means that these lines don't eventually intersect.
Oh.
Remember, we're doing a contradiction. This is an impossible picture. Does that make sense now?
Yeah.
Okay. Ask questions if you don't understand. I mean, we're in no rush. And you're the only one here that hasn't already done geometry, so don't feel bad if you need to ask a lot of questions. That's just fine. Because it's easy to forget what was hard for you when you went through a class. And so we could have forgotten what's obvious and what's not obvious when we first went through it. Okay, so that's that first thing. So there is at least one line through a point parallel to a given line. Okay? Now, this next postulate that we get is the place where our geometry diverges from what is called hyperbolic geometry. And going back and talking about Euclid had 5 postulates and 5 axioms, right? This was his 5th postulate. It didn't have these same words, but it captured the same idea. And it was, for a long time, people thought that they should have been able to prove it. So basically what they thought they should be able to prove is that if you have a line and a point not on the line, that there is only one line I can draw through that point so that those 2 lines don't intersect. Here we prove that there's at least one. But how do I know that there's not 2, or 3, or 4, or 5? Shouldn't I be able to prove that there's only one line through that point so that those 2 lines don't intersect? It should appeal to your intuition that yes, that should be something that we can prove. That should have to be true, based off of everything we've done. For over 2,000 years, well, I don't know if it got up to 2,000, for roughly 2,000 years, that's a fair way to say it, very great minds tried to prove this over and over and over again. And it turns out it's not necessarily true based on our geometry. Our geometry can now diverge into one of 2 ways. We could make so that there is only one line, or we can make so that there is more than one. And it turns out if there's more than one, there's infinite. So either there's infinitely many lines through that point, parallel to this line, or there's only one. And which one of those we choose as a postulate determines what our geometry is. So right now we're choosing between what's called hyperbolic geometry and planar well, they call it parabolic geometry, but you typically hear it called Euclidean geometry. Now we're studying Euclidean geometry. So we're using Euclid's postulate, or one logically equivalent to Euclid's postulate. But every theorem that we've proven up to this point in this class is also true in hyperbolic geometry. Now, hyperbolic geometry, it's hard for you to envision what exactly that is. In short, it's a geometry that's not on a flat surface like this. It's the best intuition for it is thinking about if our geometry were on a horse's saddle. And so if you think about it on a horse's saddle, the way I tried to explain to it, I'm going to draw a horse's saddle two different ways. I'm going to draw a bird's eye view, looking straight down on the saddle, so it's a rectangle, and then a side view of the horse's saddle, which is something like this. Right? I'm not an artist, but something like that. The point is, bird's eye view, when we talk about the distance from this point to this point, so one of those points we can see right here, we can't see the other one because it's on the other side of the saddle. That distance is smaller than the distance from this point to this point. From here going all the way up over on the other side of the saddle. So in our geometry, we want those 2 points to be the same distance apart. In hyperbolic geometry, where you're on this curved surface instead of this flat surface, or like the whiteboard, then those 2 points, even though we can make parallel lines here, that distance and that distance are very different distances. And so if we were to try and draw a line that stays the same far away from this line, it might actually look more like this. Let me see how I would do it. I don't know, something like this. And on the side of the saddle, it would look something like this. These are the points that stay that far away. And if on a bird's eye view, it would curve in like that as we go. Does that make sense? So that's a different type of geometry. The one we want is planar geometry. We want Euclidean geometry, where if you have 2 parallel lines and you go and you take sets of points opposite each other, or if you draw a line perpendicular, we won't explain too much what we mean by that, just give you the intuition. We want parallel lines basically to stay the same distance apart. In hyperbolic geometry, that's not necessarily the case. The distance between them could grow. And that's why you can get infinitely many lines for a given line parallel to it. Does that make sense with the picture of the horse's saddle, what I mean there? They always use a horse's saddle, but they probably do that because for a long time, that's how people got around. They were very familiar with their horse's saddle. Probably need a new analogy nowadays. But that's a common one that's given. Probably mostly for historical reasons. So, this is by far Euclid's most famous postulate. It's always referred to as Euclid's fifth. Tons of research has gone into it. And for roughly 2,000 years, no one seriously considered the idea that there could be more than one line through it. And your book gives a brief historical note about the 3 mathematicians who first considered that. 2 of them who actually published it. The other one was Gauss. And because hyperbolic geometry disproves Immanuel Kant's philosophy of transcendentalism, if you've ever heard that. And Kant was a big deal in his day, and he didn't want to oppose a big deal politically. He never published his work. So he went and explored all this and never published his work. One of the guys who did publish it showed it to Gauss, says, look at how cool this is. He said, yeah, I've already explored that, but good job. Here's your golden star. Anyways, just history. A lot of history behind Euclid's fifth. So this is our last postulate for planar geometry. We won't introduce any more until we go to 3-dimensional space. But as long as we're in 2-dimensional space, that's now the last one. And it's the last postulate Euclid introduces in his Elements. He held off even using this as long as he could. And people speculate because he thought he should somehow be able to prove it. But he couldn't figure out how to prove it, so he finally added it as a postulate in his book. And it turns out you have to add it as a postulate. Okay. So let's move on to the next theorem. So if L, M, and N are distinct lines with L parallel to M and M parallel to N, prove that L and N are parallel. So basically proving that parallel is transitive, right? So let's draw the picture real quick. Here's L, here's M, here's N. So we know that this is parallel to this, and we know that this is parallel to this. Shouldn't matter where we draw these. But we're trying to prove that this is also parallel to this. L is parallel to N. That's parallel to that, that's parallel to that. Try and prove that this is parallel to this. Well, if L's not parallel to N, what happens?
N's not
Let
parallel.
me draw, switch N and M places so that we can keep the picture a little cleaner. If N and L aren't parallel, what does that mean? They intersect. So if L and N are not parallel, then they eventually intersect through some point A. But we have that L is parallel to M. Oh wait, let me see here. L is parallel to M, and M is parallel to N. So if those two intersect, how is that our contradiction? I'm missing something obvious. L is parallel to M. We have that is parallel to that. And M is parallel to N. Oh, there we go. And that is parallel to that. Okay, here's how we have our contradiction. So we have L and N, two lines that go through the same point, right? Parallel to M. Two different lines, parallel to M, go through the same point. Do you see it?
Yeah.
Why doesn't that work? Because you can only have one. That's what this is saying. Through a point A, not on L, through a point A, not on M this time, there is one and only one line through A parallel to this. Here we have two lines going through A parallel to this. That can't happen. There's one and only one. That's our postulate. This isn't something we prove, it's a postulate. Does that make sense? Pretty simple? Okay. Do we need to write out the proof of that? Yeah? Alright. Let L, M, and N be lines such that L, let me say it this way, M is parallel to L, and M is parallel to N. Good? So let these three lines be parallel, such that those two are parallel to this one. Good? 2. By way of contradiction, assume, what are we trying to prove? Trying to prove this.
L and N intersect.
Assume L is not parallel to N. That's how we say not parallel. We did the parallel symbol, just draw a line through it. Okay, if L is not parallel to N, what does that mean? They intersect. 3. Then L and N intersect at some point, comma, call it A. So they have to intersect somewhere. 4. Then there exists two lines through A parallel to M. Contradiction. That contradicts this. Our postulate says if we have a line and a point not on the line, there is only one line I can draw through that point so that these two lines are parallel. I can't draw another one. They'll eventually intersect. Does that make sense? You see how that's a contradiction? Good? All right, awesome. Okay, erase all that. And we'll move on. Let's see. So we did that theorem, we did that theorem, we talked about the postulate, we did that theorem. Let's do 8.3. If L is parallel to M and line N does not intersect L, all right, we'll write it out and draw the picture for it. So theorem 8-3, it says if L is parallel to M and line L not equal, N not equal to L, so some other line that's not L intersects L at some point P at some point P, comma, then N intersects M. So let's draw a picture of it. Our picture of it is we've got some point or some line L, some line M. We know that these two lines are parallel. And we're saying that some other line N comes along and it intersects L at P. We're proving that it also intersects down here at M. Does that make sense? All right, so let's think about that one. We're trying to prove that if that intersects that, then it has to intersect down here. Just see how he does it? Given, L is the only line on P parallel to M. Yeah, that's true. Oh, sorry. Okay. So, here's a line M. Here's a point P not on M. L is a line through P not on M. L is a parallel line through P not on M. There is only one line through this point parallel to M. That's our postulate. P also, or N, sorry I didn't name that. N also goes through that point. Therefore, N can't be parallel to M. Therefore, it has to intersect it at some point.
Oh.
Right? Need to write it out? Yeah? All right. 1. Let L, wrong L, let L and M be parallel, and let intersect L at P. Okay, just setting up our picture. Then, well, let's do it this way. Assume, by way of contradiction, that N is parallel to M. So if N is parallel to M, why is that bad? So if we say N is also parallel to M, why doesn't that work?
It can't intersect L.
What does our parallel postulate say? It says if we have a line and a point P not on the line, then there's only one line through this point parallel to this line. So N can't be parallel to M because L is already parallel to M. Does that make sense? All right. So assume by way of contradiction that N is parallel to M. 3. Then M and N, or sorry, L and N are both lines through P parallel to M. Contradiction. That contradicts our postulate, right? 4. Therefore, N is not parallel to M, and so intersects it. Does that make sense? It's not parallel, so it has to intersect. That's what it means to not be parallel. Okay, that's that one. Next theorem. Theorem 8.4. Let L1 and L2 be lines cut by some line L. If L1 is parallel to L2, then the two alternate. Okay. Oh, we need our definitions first, and then we can talk about that. So I'm not going to write out words for all these definitions. I'm just going to draw the picture and then walk you through what they are. So if we have 3 lines, all intersecting like that, let me name my angles the way that they do. 1, 2, 3, 4. So they call this angle 1, angle 2, angle 3, angle 4, angle 5, angle 6, angle 7, and angle 8. So definitions. First off, we have what's called corresponding angles. So 1 and 5 are corresponding angles, 2 and 6 are corresponding angles, 3 and 7 are corresponding angles, 4 and 8 are corresponding angles. Oh, maybe we should start with transversal. So if I had 2 lines, L1 and L2, then this new line, L3, is called a transversal. It intersects both of them. So given 2 lines where we have a transversal line go through them, then it gives us these types of angles. So our names for these angles are corresponding angles. It's just a name for them. So when I say the corresponding angle of angle 1, you know I'm talking about angle 5. If I say the corresponding angle of angle 3, I'm talking about angle 7. Perfect. Okay, so that's corresponding angles. Next thing we have are alternate angles. The alternate angles you can think about as finding its corresponding angle, then take its vertical. So the alternate angle of 5 is angle 3. The alternate angle of 6 is angle 4. The alternate angle of 2 is 8. Perfect. So we have corresponding angles, we have alternate angles, And then we have interior and exterior. We call these ones the interior and these ones the exterior. So, what was the alternate angle of 5? 3. So we call those ones alternate interior angles because they're alternate and they're interior. And 6 and 4 are alternate interior angles. And then 2 and 8 and 1 and 7 are alternate exterior angles. Good? Just definitions, terminology. You'll probably get more comfortable with talking about these things as we go on proving them and using these words over and over again. And then, now I'm thinking we skipped definition. What was definition 8.2? Yeah, we didn't talk about direction. Remind me to go back and talk about direction after we get done with this. Okay, all right, so that's terminology. Now let's do Theorem 8.4, and then we'll go back and talk about direction. So, Theorem 8.4 has a lot of words. Let L1 and L2 be lines cut by line L. When we say cut by line L, that's the same thing as it being a transversal. So, we'll erase that and we'll draw a picture, and I'm assuming L1 and L2 are going to be parallel. Oh, if they're parallel, then we're going to prove something. So, here's what our picture is going to be. L1, L2, and then they're going to be cut by L. So L is going to be their transversal. So let's see. Oh, turn the page. If L1, do one of you guys just want to read it to me and I'll write it as we go?
Let L1 and L2 be lines cut by
Let L1 and L2 be lines cut by
line L.
L.
If L1 is parallel to L2, then two alternate interior angles are congruent to each other.
Are congruent.
And it says and conversely.
And conversely. So replace our. If that, why they worded that way. L1 is parallel to L2 if and only if the two alternate interior angles are congruent. Right? So that's saying we need to prove that this is parallel to this if and only if this is congruent to this and this is congruent to this. So we need to show that if this is true, then that's true. And if that's true about the angles, then the two lines are parallel. Okay? So let's see. Start with the forward direction, I guess. Forward direction. 1. So if the two lines are parallel, we need to prove that their alternate angles are interior. So let's start with that proof. So all we know so far is that those two lines are parallel and that L intersects both these. So here's my thought process for that, similar to what we already did. I'm going to say come up here and make an angle using this ray. Make an angle congruent to this angle. So we've got this angle right here. I'm going to come up and make some ray here so that that is congruent to that. And I'm going to show that this side has to be the same as this. So I know if I make that angle congruent to that angle, we already proved that these two lines have to be parallel, otherwise they meet and intersect, which gives us a triangle with a larger exterior angle. So using this ray, I have this line and this line. I know that this line and this line are both parallel to this line. Therefore, they have to be the same line. You see my thinking there? So that's how I'm going to do that one, and then we'll see how I do the next one. Not sure yet. Now I've got to name things and make everything messy. So let's see. We'll call that point A, we'll call that point B. We'll pick a point here, C, and then we'll come up here and construct an angle congruent to BAC using points, extend that some, here's L, using points A, B, C, D, and E. Okay, so let's start with that. So 1, let L1 parallel to L2, comma, and let L cut L1 and L2. So cut just means intersects both of them. 2, let A and B be the points where
L2 and L1 intersect.
L intersects L1
L2.
and L2.
Say L2 first.
L2 and L1, respectively. But I won't write that. Good catch. So then, we've got those points named. Now we need to say, let D such that ABD and let C be some point on the side of AB, and then construct this angle on that same side. So 3, let D such that ABD, so just some point up there, and let C be any point on L2 not equal to A, and let C not equal to A on L2. Notice we don't really care if C is over here or over here. If C is over here, we just need to pick E over here as well, so that this angle is congruent to this angle. So we don't really care which side C is on, doesn't change our proof. So 4, let C on the same side of AB, or of L, I guess, on the same side of L as C, such that this angle is congruent to this angle, such that angle DBE is congruent to angle BAC. Good? And then I'm just going to say by, what was the theorem where we did that? By theorem, I think it was the first one we did, or was it the second one?
Alright, the first.
8.1 or 8.2, one of them. Call it 8.1. By theorem 8.1, line BE is parallel to L2. You remember that? maybe we'll go over that one more time, draw a separate picture down here. So we said, if we have, here's how we did it. We said, take a point not on a line. Pick some point on the line. Construct this line. Now, we have an angle, right? Come up here and construct another line so that this angle is the same big as this angle. And we said now these two lines have to be parallel, because if they're not parallel, then they intersect eventually. Just draw it like that. Then they intersect eventually at a point P, making a triangle that has an opposite interior angle congruent to its exterior angle, which doesn't work. Notice that if it intersected over here, we could have this, we have the exact same argument. Because if that's congruent to that, then this is congruent to this. Because they're supplementary angles. Right? So, if this angle is congruent to this angle, then this line, L1, or sorry, not L1, BE, this line, has to be parallel to this line. Does that make sense? So by theorem 8.1, line BE has to be parallel to line L2. 6. Since BE is parallel to L2, and BE, well, I don't know, what's the best way to explain this? I want to say, look, BE and L1 both intersect B and are both parallel to this line. Therefore, they're really the same line. Right? There is only one line through this point parallel to this line. There's only one.
E5.
Huh?
Postulate E5.
Euclid's dead. So, that means that this line and this line really have to be the same line. Because there's only one line that goes from point B parallel to this line.
Yeah, but what if it intersects it, so it also intersects that?
You're saying, what if this intersects this? So if this comes down and intersects this line,
Why can't it do that?
so notice this angle is the same big as this angle, right? So the supplement of this, let's pick a different color to help you see this. The supplement of this is this angle right here. Right? And it has to be congruent to this angle right here.
Oh.
Same thing we talked about down here. So by this theorem, we already know that this line has to be parallel to this line. Right? And we already know that L1 is parallel to this line.
And then we'll go through.
So line BE is parallel to L2, and line L1 is parallel to L2. And they both go through the same point B. So we have two lines going through the same point parallel to our given line. Therefore, they have to be the same line. Because there's only one line that can do that. That's our postulate. Does that make sense? Perfect. So get rid of the, who cares if it's there? I mean, not like this is for anyone but you guys. You understand what I'm saying. So since BE is parallel to L2, and L1 is parallel to L2, and BE and L1 contain point B, comma, then BE is equal to L2. They're the same line. Or L1, sorry. Did I mix up my L1s and L2s as I was talking? Since BE is parallel to L2 and L1 is parallel to L2, then BE and L1 are the same line because they both contain B. Does that make sense? Okay. So we just proved that if Oh, we proved if we have two parallel lines, then this angle is congruent to this angle. So this line's really the same as this line. That's what we just really said. So our picture looks like that, right? So we proved that this angle is congruent to this angle. That's almost what we want. We're trying to prove that this angle is congruent to this angle. Shoot. How are we going to make that leap? We know this angle is the same as this angle. So we know that E's really down here. So I know this angle is the same as this angle. I'm trying to show this angle is the same as this angle.
Use the vertical angles there.
Yeah, vertical angles. Vertical angles are congruent. This angle is congruent to this angle. So this is congruent to this is congruent to this. You remember that? Okay. So we got this is congruent to this, and then we can do the exact, well, we don't even need to use the same argument. This is congruent to this, and so they're adjacent supplements. Move B, get rid of blue, right there for a second. And so their supplements are also congruent. We also have that. Right?
Yep.
So we have that's congruent to that, and so their supplements are also congruent. We already have that as a theorem. So we just really proved alternate interior angles are congruent when you have two parallel lines. If you have two parallel lines, then their alternate interior angles are congruent. Now we need to show it the other way. We need to show that if your alternate interior angles are congruent, then you have parallel lines. So we proved it this way. I didn't finish writing it, did I? But you see how to do it. I'm not going to finish writing. So now let's prove it the other way. So let me erase my picture. Let's just start over. The other way is a lot easier, so I probably don't even need to write it. You'll just see it. So this time we're saying we have L1 and L2. We don't know that they're parallel. That's what we're trying to prove. What do we know? We know that for some line that intersects in L, we know that this angle is congruent to this angle, and this angle is congruent to this angle. Right? So, using vertical angles, this angle is the same as this angle. So this angle and this angle are the same. And for the same reason, these two lines have to be parallel. Because if they weren't, then we either have a point over here, making this triangle, or if you think about, okay, we've got this vertical angles, L1 and L2. So we've either got a point over there if they're not parallel, or we have a point over here if they're not parallel. Either way, we construct a triangle that has an exterior angle congruent to one of its opposite interiors. If it's this point over here, we've got that congruent to that. If it's this point over here, we've got that congruent to that. Either way, it doesn't work. So they're parallel. Does that make sense? Do we need to write that out? You got that one? Okay. So that one's a lot easier that way, so that's why I want to start with the harder one. Oh yeah, definition of direction. Thank you. So, we use rays to designate a direction. It's a very natural thing to want to do. It should be kind of intuitive to you. What do you usually use to indicate a direction? An arrow, right? You usually use an arrow to indicate a direction, which is a ray in our geometry. That captures the idea of a ray. So we say two rays are pointing in the same direction if, so here's two rays. We said they're pointing in the same direction if you were to draw a line through both their vertices, these two rays are parallel and on the same side of this line. So these two rays are pointing in the same direction if they're parallel, since they're on the same side of that line. If I had two rays that were parallel, but on opposite sides of the line, they're not pointing in the same direction. So if I have two rays that are pointing in the same direction, that means that if you were to draw a line through both their vertices, they would be on the same side of that line, and the lines you could get by extending the rays are parallel to each other. That's what it means to be in the same direction. Does that make sense? And it's pretty natural, right?
Yeah.
Pretty natural definition. And then this is why we force them to be on the same side of the line. Because you would not want to say that these two things are pointing in the same direction. Those two things aren't. Okay, last direction. Now, moving on to Theorem 4 is what we did. Our next definition, sums of angles. Now, I didn't know that this definition was coming, so we've kind of already been talking this way. So when I want to talk about, so if I have two adjacent angles with a common vertex, so, well, I'll just label them here. Oh, I'm going to need to actually do points. A, B, C, D. Well, I probably don't need that. I can just type it. We talk about the sum of angle ADB. The sum of this angle and this angle is this angle. And we've kind of been using that terminology with, if you remember back to how we talked about if we had two angles, two sets of angles like this, D prime, A prime, B prime, C prime. And if you had any combination, one of the combinations is if this is congruent to this, and this is congruent to this, then that whole thing's congruent to that whole thing. You remember that? And we had if that whole thing's congruent to that whole thing, and that's congruent to that, then this piece is congruent to this piece. And we already were using the words the sum and the difference, or adding and subtracting angles. So now he's given you a definition of sums of angles. So maybe read it exactly. Well, you can just look at the picture. Looking on page 142. So he uses O and ABC. So I'll just draw the picture and then read it out and make sure we completely understand it. So his picture is this. We have O and then A, B, C. So here's his definition looking at that picture. If angle AOB and BOC are adjacent angles, and either angle AOC is a straight angle or OB is interior. Maybe it's a good thing we read this so I can talk about the difference there. So there's two pictures that we need to have in mind. We have this picture where OB is interior, or we have this picture where AOC is a straight angle, and then it doesn't matter where B is. Isn't B still interior to angle AOC if we draw it right there?
No, the interior is the damn side.
The interior is down here, and this is the exterior? No. A straight angle doesn't have an interior or an exterior. It's one of the things that we went over and over again when we introduced the definition of an interior angle and an exterior angle. Do we need to talk about that definition one more time? What's the interior of an angle? So if I have some angle composed of two rays, R1 and R2, the interior is all the points on the same side of R1 is R2. So that gives us all these points. All the points on the same side of R1 as R2. R2 is on this side of R1. So it's all those points. And all the points on the same side of R2 as R1, which is these points. So the intersection of those is just this. You see that? That was our definition of interior. So now let's think about that when we have a straight angle. Here's R1, here's R2. Take all the points on the same side of R1 as R2. Is R2 on the side of R1? No. So the definition breaks down. So straight angles don't have an interior. So our definition is saying, if we have two adjacent angles, so notice in both these cases, that angle and that angle are adjacent, that angle and that angle are adjacent. So AOB and BOC are adjacent in both these pictures. So if we have two adjacent angles, and either OB is the interior of AOC, or AOC is a straight angle, you see how we're still talking about one of these two pictures? And then it's just going to say, then the sum is AOC. Then the sum is AOC. So let's read the exact verbiage one more time. So if angle AOB and angle BOC are adjacent angles, and either angle AOC is a straight angle, or OB, the ray OB, is the interior of angle AOC. OB is the interior of angle AOC, so we have one of these two pictures. Then we say that angle AOC is the sum of angle AOB and BOC. Does that make sense?
Yeah.
And it says, likewise, if we have angles congruent to these things, then we can still call the sum of that thing. So maybe I'll specify that. But first, let's get this down, and then I'll go figure out what that's saying. So maybe start with a question to see if you're catching the definition. What's the biggest angle we can possibly get adding angles together? What's the biggest sum of angles we can get?
AOC? Or, right?
A straight angle is what I'm going for.
Oh.
We can't ever get the sum of angles to give us more than a straight angle using this definition. Does that make sense? Okay. So it says that this is the sum of these two angles, or this is the sum of these two angles, and then it has a second part where it says, or if you have the case where we have some angle here congruent to that, and some other angle here congruent to that, I know I didn't draw them very well, then this angle is also the sum of these two separate things. Does that make sense? So these two angles don't actually have to be adjacent like this. It's just if you were to draw angles congruent to them adjacent like this, then the resulting angle is still their sum. That's what it's saying. Does that make sense? So you don't have to have two angles right next to each other to sum them. You can make two angles congruent to them right next to each other, and then sum their congruent angles instead. Does that make sense? Okay. That's all it's saying. It's kind of a lot of verbiage, but if you understand it, it's actually pretty simple what's saying. So if you don't perfectly understand it, ask questions now, because it's a simple idea. I'm just not explaining it good enough if you're not getting it. No, yes, you got it? Kinda. If you only kind of got it, then you don't got it. Let's say we had numbers. If this was 30 degrees, and I hate doing this, but we'll do it, and this was 20 degrees, then their sum is a 50-degree angle. So we're saying you can take the sum by just looking at this whole angle right here, or if this were 30 degrees over here, and this were 20 degrees over here, what's the sum of these two things? It's still 50. So they're saying, how do we get an angle that's the sum of these two things? How would I draw that angle? They're saying, stick those two angles right next to each other. Then the angle that they make is their sum. That's all it's saying.
Okay.
Is that better? You think you got it now? It's not a hard idea if you understand it. So if they're right next to each other, then their sum's that whole thing. And if they're not right next to each other, just draw ones that are right next to each other that are the same size, and then their sum is that whole thing. Good? All right, perfect. That's weird. Okay. And then two more definitions that I feel like we've already been using, but he introduces them once again. He says if the sum of two angles is a right angle, so if together two angles make a right angle, then we say that those two angles are complementary. And if two angles together make a straight angle, then we say that those two angles are supplementary. So if the sum of two angles is a right angle, those two angles are called complement angles. 30 degrees and 60 degrees are complement angles, because together they give you a right angle. 100 degrees and 80 degrees are supplement angles, because together they give you a straight angle, or a 180 degree angle. Now we don't have a definition of degrees yet in this class, but we'll get to how you measure angles. That will come later. But that's what we're going to ultimately end up with. Good? So, just more terminology. And now, we'll do a useful little theorem that you guys already have probably memorized the results to. How many degrees are in a triangle? 180. You don't just remember that?
I do. I was waiting for her to say it.
Oh,
Since it's
she
so
hasn't
long.
done geometry yet, so she probably doesn't remember. But yeah.
I just wasn't sure.
Oh, so you have heard that.
Yeah.
So let's prove that real quick. We're not going to prove it's 180 degrees. We're going to prove that the sum of the angles in a triangle is a straight angle, which we'll later demonstrate is 180 degrees when we give our definition of degrees. But so let's do that. So here's how we're going to do that. We're going to say, here's some triangle ABC, doesn't matter how we draw it. I'll do my A up here, and then BC down here. We know through A, there is one and only one line parallel to BC, right?
Yeah, right.
So let L be the point through A parallel to BC. Good? And maybe think about extending that line. And now we have two transversal lines. We have AB here. Maybe we'll think about that one first, and then we'll look at the next one. So this is a transversal on these two lines, which means its alternate interior angles are congruent. So that means that this angle is congruent to this angle. Good? Now, thinking about extending this line, we once again have that's a transversal on two parallel lines, so its opposite exterior angles are congruent, which gives us that this angle is congruent to this angle, right? And then this angle is congruent to itself. So this angle plus this angle plus this angle is the same as this angle plus this angle plus this angle. So the sum of those three angles is the same as the sum of those three angles, which is the straight angle. You see that? Pretty simple proof, but it's pretty neat. Do we need to write that one out, or is that one pretty obvious? Cool. So that was theorem 8.5. The sum of the angles of a triangle is a straight angle. Yeah. Alright. Next, we've already talked about what a polygon is. We talked about a polygonal path, and then we made the definition of a polygon from it. So first we said, take n points. Some number of points n. So here's P1, here's P2, here's P3, here's P4, P4, and take some number of points all the way until we get to Pn. Some number and a point. If we connect all those points with segments, then this is a polygonal path. Okay? If the path starts and ends at the same point, so maybe Pn was actually also right here, so that it suddenly jets back, like that, that is called a polygon. Okay? Now, we're going to come, we already went over that definition. Now we're going to come up with what's called a simple polygon. So, let me read the definition and then I'll explain it with a picture. A polygon is a polygonal path whose beginning and end coincide. That's why I drew here. A polygonal path whose beginning and end are the same point or coincide. If the vertices are all different and no two sides, each one of these segments is called a side of the polygon. Does that make sense? So P3 to P4, that's a side. P4 to P5, that's a side. P1 to P2, that's a side. So let's read it again. If the vertices are all different and no two sides have a point in common, then the polygon is called simple. So it's called a simple polygon, basically, if we don't have any sides intersecting. And none of the vertices are the exact same vertice. So none of the points are the exact same point, and none of the sides intersect. So what's an example of a simple polygon? That would be something like this. That's a simple polygon, but if instead it went like, I don't know, this, that is not a simple polygon because the sides intersect. Good?
Yeah.
So that's a simple polygon, and then don't they do convex? Oh, they do it as the next definition. So that's definition 8.7, and then there's definition 8.8, and then definition 8.9. Let's get to definition 8.9 real quick because it makes sense. So this right here is a simple polygon. It's called a convex polygon if for any 2 point, maybe be real clear really quick, is this a point on the polygon? Is it?
Yes.
Yeah? Is this a point on the polygon? No? Is this a point on the polygon? That's not on it? No. Great. That's not on it. The polygon is a set of all these points out here, right? So here's what it means for it to be a convex simple polygon. It's convex if for any 2 points you pick on the polygon, A, B, any 2 points you pick, then the segment right there that those 2 points make doesn't intersect the polygon, except at the points A and B. Let me read the exact definition real quick to make sure I didn't miss some small point. Now, I'll give you an example of convex versus not, and I have completely lost my page. Here we are. A simple polygon is called convex if, whenever A and B are points on the polygon, every point of the segment AB lies either on the polygon or in its interior. That's how they say it. So AB either is on the polygon. The case where it would be on the polygon is if B was right here.
They're on the same side.
So if A and B are on the same side, then notice their segment lies completely on the polygon. So if for any 2 points AB that you pick on the polygon, if their segment either lies completely on the polygon or on the polygon's interior, how would we define the interior of the polygon? We take the interior of that angle, the interior of that angle, the interior of that angle, and etc. And take the intersection of all those. But you have good intuition for what the interior of the polygon is. Then this is called convex. Let's give you an example of a polygon that's not convex. This one is not convex. Why is it not convex? If I pick a point A here and a point B here, is there a segment on the interior? No.
How do you define the interior in that case?
The intersection of this angle with the intersection of this angle with the, oh, I don't know. How did we define the interior? I mean, I could think of a way to define the interior. Break it down to all its triangles and define its interior in terms of its triangle components. Because the interior of the triangle is the interior of all the angles. I don't remember what the definition was for the interior of a polygon. I don't know, we came across one. Maybe they're just relying on your intuition. Or maybe they give it to us in the definition. I skipped over to go to that. So let's look at definition 8.8 and we'll come back to that question. Definition 8.8. Vertices of a polygon that are endpoints of the same side are called adjacent vertices. So let's go over what that means. This vertice and this vertice, not adjacent. This vertice and this vertice, 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 adjacent. If they share, if they're both endpoints of a common side, then they're adjacent. Read the exact verbiage one more time. Vertices of a polygon that are endpoints of the same side are called adjacent vertices. Good? Angles whose vertices are adjacent to each other are called consecutive angles. So this vertice is adjacent to this vertice. So this angle and this angle are consecutive angles. This vertice is adjacent to this vertice, so this angle and this angle are consecutive angles. This vertice is not adjacent to this vertice, so this angle and this angle are not consecutive angles. Does that make sense? There's a lot of vocabulary in this chapter, so it'll be worth it to read through it on your own. Make sure you understand all the different words. And then, let's see. A diagonal of a polygon is a segment joining any non-two adjacent vertices. So let's look at this polygon. All the diagonals in this polygon, let's do it in different colors so it doesn't look like I'm changing my polygon. Here is a diagonal, here is a diagonal, here is a diagonal, here is a diagonal, here is a diagonal. All the line segments joining non-adjacent vertices are called diagonals. How many diagonals in a square? 2. How many diagonals in a triangle? 0. Good. So I think you got the idea of a diagonal. What definition are we on? 8? Oh, and then lastly, sides with a common vertice are adjacent sides. So this side is adjacent to this side, and this side is adjacent to this side. This side is not adjacent to this side. This side is adjacent to this side. This side is adjacent to this side. Question. How many sides is this side adjacent to? 2. Every side's always adjacent to just 2 sides. Good. Yeah, you didn't let his noise change your answer. That was good. You used your brain instead. Alright, definition 810. If all the sides of a polygon have the same length, the polygon is called equilateral. And if all the angles are congruent, it's called equiangular. So if I drew this pentagon so that that side was the same long as 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 that side, then it would have been an equilateral pentagon. And if I would have drawn it so that that angle is the same as 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 that angle, it would have been an equilateral pentagon. Or equiangular. Yeah, so one of the proofs that we already did in this class, or maybe it was a homework problem, was we proved that an equilateral triangle, equilateral, all the sides the same, is also equiangular. That's one of the proofs that we did.
Yeah.
Is that going to be the case with a four-sided polygon? If I have an equilateral four-sided polygon, is it also equiangular?
Four sides is a rectangle.
Four sides that are the same as a square, right? And is a square equiangular? If I have
Yeah.
four sides all the same length, then all the angles are the same length, right? No! Because I could shift that thing. I could have drawn it like this.
It's called a rhombus.
It's called a rhombus.
Triangles
So
is
don't be
right.
tricked. Equilateral does not mean equiangular. It does in the case of a triangle, but it doesn't in general. So you understand the difference between equiangular and equilateral?
Yeah.
Question, what about if all the angles are the same? Does that mean that it's equiangular? Yes?
Do you know what you just asked?
Oh, did I say it wrong?
You said doesn't mean it's equiangular.
If it's equiangular, so if we made all those angles 90-degree angles, then is it equilateral?
No.
Why not? Rectangle, perfect. Yeah. Not all rectangles are squares.
What about for odd-sided polygon?
Same thing. Easy way to think about it. Think about taking a box like that where that and that are the same, right? And then creating an isosceles triangle right here.
Yeah, I'm talking about the angles.
Right. It's possible for me to construct that isosceles triangle with side lengths equal to the square.
I know the side lengths, I'm talking about the angles. But if it's equiangular,
Oh, if it's equiangular, is it equilateral?
I assume it has to be for odd-sided polygons. Because there's no... Yeah, I assume it has to be.
That's a good question. Your intuition really wants it to be.
Because you can't squish a pentagon in any way. Like you can a square. Wait, no, I'm thinking of the wrong thing. You can't stretch a pentagon
Yeah, can you stretch a pentagon without changing its angles?
without changing any one angle.
I don't know. I can't do it in my brain.
Because you can squish a pentagon. Yes.
Yeah, it's a good question. I'm not sure. Have to think about that. Have to play with it. But my gut wants to say yes.
But even sided, you can just stretch to.
Yeah, there's always two sides that you can stretch. Yeah, it's a good question. Continuing. So we got equilateral, we got equiangular, and then we have, if it's equilateral and equiangular, then we call it regular. So a regular triangle is an equilateral triangle. A regular quadrilateral is a square, etc. And then finally, some common shapes that we reference. Polygons of 3 sides are called triangle. 4 sides are called quadrilateral. 5 sides are called pentagons. 6 sides are called hexagons. 7 sides are called.
Oh, what is that one?
Have any of you guys done organic chemistry?
Yeah.
That's where I had to learn all this.
The
Yeah.
snake.
I don't know about snake.
Wait, organic.
Hept.
Okay.
Heptagon.
It's not
8 is octagon. Nope. H-E-P-T. Hept. And then 9 is nonagon.
Oh.
And then 10 is decagon. So those are the common ones. Mon, bi, tri, quad, penta, hepta, or penta, hexa, hepta, octa, nona, deca. Yeah, that's not rude.
So what's the definition of polygon?
A polygon is a polygonal path that starts and ends at the same point.
So the smallest polygon is 3. Because if there's 2, they'd be different points.
Why isn't that a polygon?
Shoot. Because it's not a path.
I'd have to read the path again.
Yeah, what's the path?
The path was in, was that chapter 7 or 6? Let P1 through Pn be any set of n points. The set of points of all the segments, P1, P2, P2, P3, all the way up to Pn minus 1 Pn, is called a polygonal path. The path is set to join or connect the endpoints P1 to Pn.
So it's because the point is not a segment.
Yeah, you don't get any segments if you do that.
P1
So you'd
P2,
end up with an
they
empty
can't
set.
have the same.
And then you can't have a segment between 2 points and having them be the same. But why couldn't you do that?
You can't.
So I think that's a valid polygon.
But it's a triangle. It's a trigon.
No, it's not. As that point,
3 points.
that point, and then the next point coincides with the first one. They're the same point. That's 2 points.
2 points.
I don't know why that's not a polygon.
Okay, so you can't have a one-sided polygon.
Because you don't have any segments. Maybe the author didn't bother being very precise.
No, you do have segments with a one-sided polygon, because it's got one side. It's just not a polygon because it doesn't.
See, but then I don't know where he gave the interior. I don't think he gave us a definition of the interior exterior, because there's no way to do it for that. Or unless everything's the exterior and its interior is the empty set. I guess that could make sense.
The interior is the empty set.
Yeah, this has no interior and its exterior is everything that's not part of the segment. That could make sense. So maybe the author just didn't bother being very rigorous with those definitions. I don't know. Now I lost our page. What page are we on?
146.
146. So we went over definition 810. And then some brief discussion. So we've gone over the sum of the angles in a triangle gives you a straight angle, right? Well, what about in a four-sided polygon? So if I have any four-sided polygon, I wonder if it needs to be a simple polygon. Any four-sided simple polygon, so the sides don't intersect each other. What's the sum of the angles in that thing?
Well, that particular one, because that's two triangles, which each is.
Yeah, perfect. Draw one of the diagonal lines. Now you have two triangles. The sum of this angle and this angle and this angle is a straight angle. And the sum of this angle and this angle and this angle is a straight angle. Now we need to be careful because now we're being a little equivocal with the way we're using the word sum. Remember, in our definition, we can't sum to more than a straight angle. That didn't make sense. So we're playing fast and loose with the word sum here. Okay? But this is going to be, once we come up with the definition for degrees, then summing is going to work exactly how we think it's going to work when we're summing degrees. So the author just points out, be a little bit careful, but he just wants to start having this discussion of adding up the angles inside a simple polygon. Does that make sense? So when we had a triangle, we had one straight angle. When we had that, we had two straight angles. What about if I have any pentagon?
It's just three straight angles.
It's just, yeah, so you can split this up into three triangles, however you want to do it. Just draw any diagonal you want, doesn't matter which one you draw. Now draw another diagonal that doesn't intersect this diagonal. Okay, now you have three triangles. This gives us one straight angle, this gives us one straight angle, this gives us one straight angle. So altogether we have three straight angles. Does that make sense?
So they just can't cross each other.
When we draw diagonals, yeah, because we're ultimately splitting it up into triangles. And I don't know that he gives a proof that you can always do that. That's a graph theory proof from discrete math. None of you did that. Never mind. But in general, if I have an n-sided polygon, then how many straight angles does it have? So when we had, let's think over here. Here was n. Here was our angle. So when n was 3, we had one straight angle. When n was 4, we had two straight angles. When n was 5, we had three straight angles. So if I have an n-sided polygon, how many straight angles? What's the sum of its angles? N plus 2? Well, let's check that. This is 5. What's 5 plus 2?
Well,
7. Is this 7?
S plus 2. I don't know.
So it's just, you have the right idea, you just set it on n minus 2 straight angles. Does that make sense? Okay. That is interesting. Once again, lost my page. Keep going to chapter 7 for some reason. That's where my book actually opens. This is using the word sum in a different sense when we speak in the sum of two angles. Recall that. Oh, and then another interesting note. So that was summing up the interior. Now let's look at the exterior angles of those things. Maybe I'll use blue here. So what about if we were to look at the sum of this angle with the sum of this angle? Let me draw it with that angle with the sum of that angle. Maybe I'll do 2 lines to show which one we're talking about. What's the sum of those going to be?
Of just the blue?
Yeah, of those 3 blue.
It's always going to be 2 straight angles.
2 straight angles, why?
It just is.
Well, here's how I see it. Look, that and that is a,
Straight
that and that is a, that and that is a. So we have 3 straight angles. Now all the brown ones together gave us 1 straight angle. So those, that piece, and that piece is 3 straight angles. Minus all the brown ones leaves us with 2 straight angles. So in this case we got 2 straight angles. Maybe we'll write that down here. 2 straight for the blue. Now let's look at this case. Let's look at this one. This one, and this one.
Easy, 3.
What do those all add up to? Well, when you include the brown, but don't include the brown, just the blue. So subtract away the brown.
It's 2 straight angles again.
2 straight angles again, right?
Yeah.
Because when you include the brown and the blue, you get 1, 2, 3, 4 straight angles. But then all the brown we already know adds up to 2 straight angles. So all the blue has to be 2 straight angles. Okay? Now that's just a coincidence, right?
Yeah, this one's going to be hard. Give me a second.
I'm losing track of what my points were because I drew those triangles. Let me, so I can draw that a little bit better. Stick it out like that because it's going to make my picture easier to draw.
Okay.
And then we'll come along. Extend one of these lines up. We'll extend that. So now we're looking at that. Extend that. Now we're looking at that. Extend that. Now we're looking at that. Extend that. Now we're looking at that. And extend. Let's see. Extend that. Now we're looking at that. Right?
That was 33.
That's how
That
we
was 50.
Is it 2 straight angles again? How do you know? Here's the intuition that hopefully you're starting to come to. Look, how many points does this thing have? How many vertices? 5. With each of those vertices, when I give an exterior angle, that's going to have to 5 straight angles. Minus 3 is 2. Here we had 4 vertices. So we're going to have 4 straight angles. Minus 2 is 2. So it's going to be the number of vertices we have
N minus 2.
minus whatever this was. Straight angles.
Cancel our ends out.
N minus n and negative negative 2 just gives us 2s. Does that make sense? Pretty cool, huh? Far from intuitive.
Yeah, you can
Well,
flip it around.
it might be intuitive, but far from obvious, I probably should have said. So that's our facts about some polygons. And then you already know what a parallelogram is, a rectangle is, a square is, and a rhombus. What's the difference between a parallelogram and a rhombus?
This is two parallel to be a parallelogram.
Huh?
I don't have a good definition of rhombus.
So, do you know what a parallelogram is though?
Yeah.
So it's four-sided, so that this side is parallel to this side, and this side is parallel to this side. That's what a parallelogram means. Its opposite sides are parallel to each other.
Yeah.
A rhombus is a parallelogram where all the sides are equal.
Oh, okay.
So it's equilateral. An equilateral parallelogram is a rhombus. That make sense?
Yeah.
So a rhombus is a special case of a parallelogram, and a square is a special case of a rectangle. Right? And a rectangle is a special case of a parallelogram too. So a rectangle is a parallelogram with a right angle. Parallelogram has a right angle, it's a rectangle. Because if I force one of these angles to be right angles, think about me like shifting this thing until that's a right angle. Now all the angles are right angles. That make sense? So that's why a rectangle is a parallelogram with a right angle. That's its definition. Or at least, that's the definition I know. A rectangle is a parallelogram with a right angle. That's exactly what it says. Okay. And that finishes chapter 8. Pretty simple chapter as far as theorems go. Pretty dense in vocabulary. So I strongly, strongly recommend that you reread it and make sure you're comfortable with all the terms. So we just randomly go over some terms real quick. What are alternate exterior angles? Come draw. Do you know what they are?
I don't know how to explain it, but I know.
Come draw. See if you can draw. Draw over here so the camera can see, so that lazy people like Laura, Leah, Rhoda, Mim, James, Jake, Lawrence, Joanne, Michaela can all see.
Why isn't Michaela coming?
Mind your business.
Okay, okay. Okay. Okay, go. Should I label him?
Sure, if it helps explain. Pretend like you're explaining to Celesta.
Okay.
Do I need to kneel down and be short?
I'll just do the angle then. Okay, so if you take that angle, then you take the opposite of that angle, which is this one, and then the opposite of that one. Well, how do you say it?
I can't remember why I asked you to show. Do you
Adjacent
remember?
angles.
Alternate exterior than angles.
Alternate exterior
Oh,
angles.
exterior angles. Okay.
Okay. We move all the angles in here.
Okay, so you take the opposite angle.
Does alternate exterior even make sense?
There you go.
Alternate interior makes sense.
What are they? What are the alternate exterior angles? Yeah, that makes sense. What are alternate exterior angles? Let's start with alternate angles. So let's go back and just put numbers here.
Okay.
So we've got 1, 2, 3, 4, 5, 6, 7, 8. Which angles are alternate angles? Give me an example of alternate angles.
8 and 1. I mean 8 and 2. I mean 6 and 2.
6 and 2 are corresponding angles.
Okay, then 3 and 2.
No? You need one from the bottom group and one from the top group.
2 and 5.
So we're looking at this group and this group.
8 and 3.
8 and 3. No. Here's how you do it.
8 and 1.
8 and 1. You had it right in the beginning. That's the first thing you said. So take its corresponding angle and then look at the vertical one. That's its alternate angle. Now, what are alternate exterior angles?
Alternate exterior angles. So,
Okay, let's start with this. Which
wait.
angles are interior and which ones are exterior?
these ones are interior, these ones are exterior.
Okay, so what are alternate exterior angles? And? Perfect. And alternate interior angles?
6 and 3.
Uh-huh. And?
4.
5 and 4. Now, a way to help your intuition is these angles we proved are congruent to each other. So alternate interior and alternate exterior angles are congruent to each other. So if you'll intentionally draw your picture extreme, it should kind of be obvious to you which ones are congruent. This one is congruent to this one, right? So those are alternate exterior angles, and these ones are alternate exterior angles. I don't know why they're 2 tick marks, but you get the point. Perfect. Good job. So that's alternate exterior and alternate interior. What's the same direction?
Array on the same line.
Array on the same line?
On the same side of the line. On the same direction.
You can't use the word in its definition. What does it mean for 2 rays to be pointing in the same direction?
For 2 rays to be on the same side of a line but parallel to each other, right?
On the same side of a line but parallel to each other? So let's see, I've got this ray and I've got this ray parallel to each other. Here's a line. They're on the same side of the line and they're parallel to each other.
How'd they go through what?
Is that reading of it?
Huh?
Uh,
It's the line through.
2 points that.
What are the 2 points you see up there? What are the 2 points I pointed? It's these 2,
Yeah.
the vertices. So take a line through the vertices, then parallel rays whose vertices are on this, take a line through their vertices, then if they're parallel and on the same side of that line,
There we go.
then they're in the same direction.
Okay. So through the vertices.
All right, what's a polygon?
It's a polygonal path whose end point and beginning point are the same.
All right, so maybe we should have started with a polygonal path. What's that? Take m points and connect them with segments. There's a polygonal path. If the path happens to start and end at the same point, then we have a polygon. Right? Okay. What is a simple polygon? Where none of the sides intersect. Good. A polygon where none of the sides intersect. What is a regular polygon?
Is that the one where it's equal angular and equilateral?
Perfect. So what's a 3-sided regular polygon?
3-sided.
What is a 3-sided regular polygon? What kind of triangle?
Pretty normal.
An equilateral triangle is a regular 3-sided polygon. What's a regular 4-sided polygon? A square. Perfect. What's a parallelogram?
It's a quadrilateral whose opposite sides are parallel.
Perfect. And what's a quadrilateral?
See,
I get it terminology.
it's a polygon with 4 vertices.
Almost. It's a simple polygon with 4 vertices. They can't intersect. So if we have a simple polygon with 4 vertices, simple meaning they don't intersect, then if its opposite sides are parallel, then it's called a parallelogram.
Wait, you can't have a non-simple quadrilateral.
You can't have a non-simple quadrilateral. You're right.
Unless you draw 2 points and go back and forth. Oh, except the definition of something. No, the definition
Maybe it
of
doesn't have to be simple.
is vertexes can't coincide. That's what you choose from. Going back and forth twice.
Oh, you're right. Okay. What else do we have? Oh, what's a convex polygon?
It's pretty much a polygon where if you have 2 points anywhere intersecting, then it can't be on the outside of it.
Yeah, it can't be exterior. So pick any 2 points A, B. If the line segment between them is ever exterior to the polygon, then it's not convex. If it's always interior or directly on the polygon, it is convex. Is your ladder still out there?
No. That sounded like someone fell. What did that sound like?
I don't know. You need to go check it out?
This is still blowing cold air. Maybe it needs to.
Okay, well, we can call class there.